All right, welcome back, everyone. Friday, well, I guess the best day of the week, anyways, at least for me. Mondays are the worst. So, without further ado, let's get started. Okay. So, we already started discussing SRAM. We just took a look at the circuit topology with 6 transistors, and then we moved on to the transistor, right? The idea was that before we jump in and start talking about how SRAMs work, we need to talk about how the building blocks of SRAM, which is the transistor, works. So in the last class, I discussed output characteristics, and then I discussed transfer characteristics. I don't think I mentioned the name transfer characteristics, but essentially I talked about the ID VDS characteristics and ID VGS characteristics, right? So very quick recap. If you have a transistor with gate, drain, and source, you need to look at the drain to source current, which we just represent as ID, or we could have written IDS, doesn't matter. Now I'm going to plot ID with respect to VDS. I cannot unless somebody tells me what is the VGS here, right? So if somebody tells me that your VGS is greater than threshold voltage, then sure, then I have a current. And the situation would be like, initially for smaller VDS, you'll have a linear increase in current with voltage, and then it will saturate and taper off, something like that. And this is for, say, VGS1. If I give you more VGS, higher VGS, then the current simply goes up. VGS2, which is greater than VGS1, say, and so on, right? That was the simple concept. And we represent this characteristic, we mention this as output characteristics. So just make sure you remember this, output characteristics. Now, on the other hand, transfer characteristics would be, say this is gate, drain, source. This is your drain current. This is source. And I'm going to draw ID versus VGS. I have to tell you what VDS I'm working with. Say, as long as you have a non-zero VDS, something, you have something there, there will be some current, okay? It's not like VGS where you have to exceed the threshold voltage. That's only applicable to the VGS because VGS creates the channel. For VDS, the channel is already there. You just have to apply something to make the electrons flow. So when you have a non-zero VDS, up to a certain VGS, you don't expect to get any current until you cross the threshold voltage. And when you do, then your current starts going up. That's the concept that we spoke about. Okay, so let's consider that this is for VDS1. What if I apply more VDS? So in that case, your current will simply go up. VDS2 greater than VDS1. So simple enough, don't you think? And then we discussed, well, for several decades, we kind of ignored whatever happens below threshold voltage. But now that we are dealing with billions and trillions of devices and components, we can no longer ignore it. And then I gave you an example of how a billion means 10 raised to 9, and a nanoampere, which is typically the current range here below the threshold voltage, which is by all means negligible. But then when you multiply a nanoampere current with a billion devices, you immediately get 1 ampere current, okay? Which is a lot of current, by the way. And if you don't, if you don't understand why there is a lot of current, just take a look at the battery rating for your iPhone. Just Google it. And then you'll understand that 4,200 milliamp hour, milliamp basically translates to 4.2 amp hour, okay? And basically you're draining 1 amp. Just imagine that, right? So it will be extremely difficult for you to have any kind of portable wearable devices at all if your transistors are like that. So when people started realizing that, hey, something's wrong with our transistors, even when they're supposed to be off, they're leaking. So then they started looking at ID VGS characteristics in a different way. So if I ask you, if I want to take a deeper look at this low current values, and I also want to see higher current value in the same graph, what is the best way to do so? The answer should be semi-log. When you plot something in logarithmic scale, the smaller numbers and bigger numbers, they both can appear in the same graph because, there is a different scaling for both of them. So that's why when you plot them in semi-log scale, the same graph looks like this. So this is the better way of drawing IDVG for VLSI transistors. Remember that. For the transistors that we use in our portable wearable devices, your computers, your cell phone. If you are a power electronics engineer, then you would probably never have to worry about this. Just care about this type of representation. If you want, you can plot it, but that's not going to make any difference at all. You know why? Have any of you taken any power electronics courses? In a circuit, how many transistors did you deal with at a time? 100 max? 20? 10? 5? Maybe 1? Right? A few. So you could count. But in VLSI, we talk in terms of billions and trillions. That's the difference. Okay. So power electronics deal with few transistors. So even if you have 1 nanoamp leakage times 10, who cares? Still 10 nanoamp, which is negligible. But it only becomes relevant when you have a huge number coming together. So VLSI folks, VLSI engineers typically represent IDVG in this, this fashion. So if I ask you to draw ID versus VGS characteristics, if I ask you to do that for this course or any other VLSI courses, you should first draw threshold voltage, VTH. And then up to VTH, there is almost like a really sharp rise, and then it tapers off. Basically, this is logarithmic representation. But the same graph, if you plot it in linear scale, it look like this, super simple. ID versus VGS. So they're essentially equivalent. All right, so just keep that in mind, okay? There are many more concepts that we could go through regarding this steep switching, subthreshold slope, and whatnot, but I am not going to go through this for this particular course because this course is not about transistors. One more thing, since it's there in the slide, I should address the elephant in the room. There is a big equation sitting in there. You see that? I'll get back to it after the next slide. So I'll show you this slide and then I'll get back to this equation, okay? So do you see that I already covered this ID versus VDS for different VGS, right? So it's already done. The only thing that we need to cover is this equation. All right, so let's first get to this table and tell you what this represents. So remember your ID VDS characteristics. And I told you that initially there will be a linear mode. And then when you apply high enough VDS, it will saturate. So you are looking at two modes of operation for transistor, linear mode and saturation mode. If I try to represent ID in an analytical fashion with some equation, this is how it looks like. For linear mode, this is your expression where you have VGS, VDS, threshold voltage, width of the transistor, length of the transistor, oxide capacitance, blah, blah, blah. All those good stuff. If I ask you to represent the saturation mode current, this is the equation. Obviously, I'm not going through the details of derivation or anything, just wanted to show you that we know equations for linear mode and saturation mode. There is one more mode, by the way, for the transistor. When your VGS is less than threshold voltage, we call it cutoff mode, typically. So in cutoff mode, notice this is not really equal, it's almost equal to 0. So the current, typically textbook will show 0, but practically it's not really 0, as I told you, right? It's like very close to 0. Okay, now setting that aside, what does it really look like? It's not really 0, right? These are older textbook, by the way. So this cutoff mode current will actually be like this. That's why this equation was there. It's so complicated. So essentially, below threshold, a lot of action occurs. And by the way, whenever you talk about something increasing dramatically, we often use, there has been an exponential increase in crime rate. Don't you think? Exponent is always attributed to something that is dramatically changing. And linear, oh, who cares about linear increase? It's like boring, right? So similarly, notice, essentially, the dependence of drain current on drain voltage or gate voltage is almost linearly dependent, or at best quadratic square. This is at best quadratic to linear, not beyond that. But here, notice this is drain current related to VGS. And notice VGS is actually within an exponent. So e power VGS or something. There are other stuff, but VGS is a power of exponent. So that means current is exponentially dependent on VGS. So basically, drain current is even more responsive to VGS below threshold, which we have kind of ignored for the most part of electronic life cycle. Does that make sense, folks? So there is an entire field of VLSI that deals with sub-threshold circuit design, where they try to achieve interesting circuit features working within the sub-threshold level. Yes. Great question. So that notice this M is coming up in several places, right? That will make me explain a few more things, which I am happy to do so. So what I will do is I will give you some hint today. And then what I can do is I can share a written derivation that I typically use for 433, because I have them derive this, by the way. So let me first give you a high level overview. Subthreshold slope, which I didn't talk about so conveniently, is a very important parameter for transistors. And what is it? Then what does that name suggest? This is subthreshold, don't you think? Anything below threshold is subthreshold. And do you see that there is a slope here? It's kind of like an ideality factor that you have in diode, right? But it's not really exactly that. Okay, there is a difference between. It's known as literally, you know what it is called? The M. It's called the M factor. I'm not kidding. It's really that. And I can show you a textbook where they have a specific chapter on the M factor because it's so critical. I mean, I was like, okay, just put it under the rug and move it. But it is actually quite fascinating. It is one of the topics of very exciting research nowadays. If you Google steep switching transistor or Bayes-Boltzmann transistor, or like they have different names. Different research groups will use different names. Or sub KT over Q transistor, they are all the same. They basically try to achieve a steeper slope here. And since there is no harm spending 10 minutes discussing this. Okay, this is a great question. So if you guys pay attention, I'm happy to explain something. Are you willing to hear? Okay. It's actually very interesting. Let's see. Imagine you have a transistor, looks like this. And I have another transistor that looks like this. So you have the same on current. The only difference here is, can anybody comment what the difference is? Sub-threshold slope. Basically, there is a slope below threshold. That's why sub-threshold slope. And which one is steeper? The green one is steeper. We can visibly see that. Do you think that's a good sign or bad sign? Why do you think so? Perfect. Yes, you guys are all correct. There are different ways of looking at it. Okay, first of all, at the very least, notice what is the off current. Whenever you this is VGS, by the way, forgot to write. Whenever you have zero VGS, that means your transistor is off. But still, you have a non-zero current. Your current is not really zero. But the lower that non-zero current is, the better it is. You have lower leakage, right? At the very least, steeper switching leads to lower off current. Okay? Does that make sense? Okay. All right. That means we would love to have transistors that have steeper subthreshold slope. Turns out there is a physical limit to the subthreshold slope that you can achieve. You can, what if I told you this green one will not exist? I mean, you cannot have a transistor in conventional semiconductor technology that will give you the green version. You can only live with the yellowish version, say. Wouldn't it be, you'd be like a little bit, disheartened. Oh no, I want that, right? So that's exactly what engineers are dealing with. Basically, this is called breaking the Boltzmann barrier. So the barrier that I told you about, the fundamental limit, that is imposed by Boltzmann limit. Okay, and that comes from the band diagram. And I don't know how if you guys have taken courses where band diagrams were covered, so I'm not getting into the detail of it. But typically, it's the fundamental limit. So since this is fun, when I say fundamental, it comes from physics. It's not from engineering, that we cannot make a good enough transistor. No, it's not us. Physics will not allow you to do that. So engineers said, challenge accepted, right? Let's beat physics. So that's the thing. If something cannot be done, let's change the physics. Instead of using conventional semiconductor-based approaches, people started taking up completely different routes towards designing transistors. And I'm going to give you some names. If any of you are interested, just look them up. Tunnel FET beats the Boltzmann limit. NC FET, negative capacitance transistor. Impact ionization FET. Okay, hyper FET. So basically, hey, you cannot beat this limit. Okay, challenge accepted. And like there are so many ways that you can break the limit. But remember, you cannot break the limit with conventional CMOS transistor. That's true. So you have to go beyond conventional CMOS. Now, getting back to the point, this M parameter that you asked about, this is actually inherent in determining the subthreshold slope. And it is basically 1 plus C1 over C2. And what's C1 and C2? Let me explain that. In a transistor, you have source, drain, or maybe I have a transistor image right here. Yeah, there you go. Notice that. You guys ready? So silicon dioxide is an oxide. You have a metal here, you have a conductor here. So essentially, you have a gate capacitance. Let me just draw it here. You have a gate capacitance, which is an COX, oxide capacitance, okay? And then you have a depletion capacitance here in the channel. So basically, we represent that as surface capacitance, CS, or substrate capacitance, or semiconductor capacitance, whatever the S stands for. So M is related to the ratio of these two capacitors plus 1. Does that make sense? So basically, it comes from mathematics, blah, blah, blah. You just, what were we looking for? We were looking for, if you apply gate voltage, how much gate voltage will actually appear at the semiconductor, and how much of it will be dropped across the oxide. In making that calculation, people arrived at a situation where you had M equals 1 plus COX over CS, something like that. So this is, somebody wrote it as M at one point, but then it stuck. And they realized this parameter is the reason why you cannot have just any arbitrary subthreshold slope. Okay, so it's a really interesting mathematical reasoning, and it's not really that difficult, honestly. I'm just telling you without showing the mathematics. That's why it sounds a little bit strange. So I'm more than happy to share those mathematical steps, and then you can see it for yourself why M appears to be the limit in determining the subthreshold slope. Okay, all right. So did I answer your question? M is M parameter. It is essentially the ratio of two capacitors plus 1. Why do we care about the ratio of these two capacitors? I didn't get a chance to explain that properly, but I gave you some superficial answer. Scientists were trying to find out, if you apply a voltage, say 1 volt to the gate of the transistor, you care about the voltage that appears at the channel, but you cannot just directly inject a voltage to the channel, right? You have to apply it to the gate. So there will be some voltage drop here, and then the rest of the voltage will show up to the channel. So they were trying to figure out how much voltage will show up to the channel. And in doing so, in calculating that, they arrived at a situation where they had this term. So somebody said, oh, let's just give it a name. And that day, they just decided to use M. Okay, and for some reason, the term stuck. And that became the infamous M parameter. All right. Even to this day, all textbooks, in fact, all device textbooks use M parameter. All right. Don't worry. I'll share some more resources to clarify. And if you guys want to learn more, you can also talk to me. All right, so very quickly, evolution of MOSFET technology, obviously. I'm just gonna like fly past this one. Notice, starting from 2003 to 2014, I don't have images after this, but that's okay. That should give you some idea. Look at this number, 19 nanometer, 65 nanometer, 45 nanometer to 14 nanometer. So the numbers are getting smaller. What does that represent? It represents the gate length. So this is the gate length. Does that make sense? So your transistor gates are getting smaller. We are making the transistor smaller so that we could fit more transistors in a given chip. Notice, can anybody notice something strange here? So between these two transistors, or even three transistors, the structure was more or less the same. Source, drain, gate. Source, drain, gate. Source, drain, gate. Source, drain, gate. See? Yeah, looks a little bit different here and there. There are some more aspects here and there. But essentially, in general, higher level, they're the same device. All on a sudden, something changed here. So in 2011, we moved over from MOSFET to a different device called FinFET, like I said, right? And then this is 2014, as you can imagine. There have been two more changes ever since. So for the most modern circuits, since you will be dealing with most modern memories, they will be dealing with FinFETs mostly, okay? And don't worry, when we simulate in class using HSpice, we'll be using both MOSFET and FinFET, and I'll show you how similar they are and how easily you can ignore the underlying difference if you want to. If I ask you to draw the IDVGS characteristics of FinFET, they will look exactly the same as MOSFET, okay? So you don't care if you don't want to. Okay, so, and that's the difference, by the way. This is the bulk MOSFET structure in 3D, and this is the FinFET structure in 3D. So there is a difference. There is a 3D angle in the FinFET structure, which, you know, I'm not covering in this course, but if you want, you can take some device courses to cover. So I'm going to quickly move over. See, I'm done with transistors so conveniently because I want one of them and another one of them to connect together to make an inverter. You see why I'm going with it? In an SRAM, like I said, there were two inverters that were back-to-back connected. So I'm quickly going to the inverter so that I can get back to SRAM. Okay. So what is an inverter? An inverter combines an N-type MOSFET and a P-type MOSFET together, NMOS and PMOS together. And this is basically the simplest possible CMOS circuit that you can create with NMOS and PMOS. Super simple. But that's also one of the most critical circuits, which I don't want to get into the philosophy of. So let's quickly talk about how this circuit works. When you provide an input, say if you apply a positive voltage, 1 volt, NMOS and PMOS transistors are complementary. Whatever, say for example, if one of them, like NMOS, turns on with positive voltage, PMOS will turn off for the same voltage, and vice versa. If you apply 0 voltage at the gate, NMOS will turn off, but PMOS will turn on. Okay? In case you haven't seen this circuit, I know some of you haven't taken these courses. Just wanted to point out, you have VDD, which is the supply voltage, and ground here. NMOS is connected close to the ground, and PMOS is connected close to the VDD. That's kind of always the norm. And there are reasons which I can ask the 335 folks about and see how much they remember. How many of you remember between NMOS and PMOS, which one is good as a discharging switch? Which one do you use to discharge a node? Did we discuss this in 335 or no? Yes. Yes, question. So you basically, it's the same thing expressed in different ways. Producing strong one, meaning charging a node. Remember, 1 and 0, they're basically representation of something physical. And what is that physical quantity? Charge. So we basically charge up capacitors. You might be wondering, where is the capacitor? There is, oh, look at that. There is an output capacitor right here. Okay. That doesn't mean we connect a capacitor with NMOS and PMOS. You might be wondering, oh, that means an inverter has three components. You have an NMOS, you have a PMOS, and you have a capacitor. We do not connect that capacitor. You get it for free. And there was 335 again. There was another lecture where MOSFET is full of capacitance. They're everywhere. So when you connect two MOSFETs together, their drain capacitors will come together and make an equivalent load capacitor. So you get it for free. So when I say we create one, a strong one, that means we can charge up the capacitor from VDD. So that means this becomes VDD when you charge it up. And VDD is represented as logic 1. Okay? Even if your VDD is 0.5 volt, we represent that to be logic 1. Similarly, when you discharge that node, when you discharge that capacitor down to ground, you get 0 volt almost. And that 0 volt is typically representative of Boolean logic 0. Does it make sense? So essentially 1 and 0 represent whether the capacitor is charged or discharged. So inverter basically inverts what you give it. So if you provide logic 1, and I'm going to make a difference between logic 1 and the physical quantity, right? Logic 1 represents VDD, the supply voltage, and logic 0 represent actual 0, ground. Okay, so I'm going to provide VDD as an input. What do I expect at the output? Anyone? 0, because it's inverter, it's supposed to invert what I'm providing. And here is how it does it. When you apply VDD, NMOS turns on, PMOS turns off. So notice this NMOS is connected to this capacitor. Imagine this capacitor was charged before. If it were not charged, that's fine. Then you already have 0, right? But if it were charged, now that the NMOS is on and it is connected to ground, this NMOS will discharge the capacitor. Transistors are like switches. They just connect different nodes. That's all. So when the NMOS is on, it will connect the capacitor to ground and discharge the capacitor. And you will get 0. So that's how when you apply VDD, you get 0. This circuit inverts. Let's see the opposite. When you apply 0 as an input, okay, let's apply 0. Then NMOS turns off, but your PMOS turns on. So notice your capacitor is now directly connected to VDD. So it doesn't matter what charge it was storing before. Now it will be fully charged to VDD. Oh, wow. You applied 0 as an input, but your output now became VDD inverter again. So that's how a CMOS inverter inverts. You could represent that using this simplified version, as if NMOS and PMOS transistors are switches. Okay, so one of them will be active, the other one will be off. They cannot be simultaneously on, in theory. Am I making sense? Okay, that's the basic concept. Now, let's look at the transient characteristics with respect to time. Okay, imagine this is a pulse that you're giving. Input, high, 0. High voltage, 0. And so on. So when you apply this high voltage to the input, what do you expect at the output? Low, 0. And that's what you get here. When you apply low voltage at the output, what do you expect? Sorry, at the input, what do you expect at the output? High voltage. And that's what you see here. Well, ideally, this could have been like a square pulse, but practically, notice instead of just creating a square pulse, we have shown some sort of delay. So it gradually goes down and gradually goes up, gradually goes down, gradually goes up. Why is it doing things gradually? Yes, thank you. It's a RC circuit. Even if you want to make it even simpler, it's a capacitor. Capacitors cannot be like instantaneously charged. It takes some time to charge or discharge. That's what you see here, the output. So it takes some time to go up or go down. That's why the delay comes in. Are you guys all with me so far? So when I learn to distinguish between DC and transient, because we'll be using it quite often in the circuits that are coming up. On your right, you are looking at a DC characteristics. What do I mean by DC? There is no time involved here. So we will not understand any delay. Some people, I mean, I asked students that, hey, see, oh, I haven't even explained it. How can I ask you this question? Okay, give me 2 more minutes. Let me first explain it, then I'll ask you that question. So look at that red line, okay? In the x-axis, you have input. On the y-axis, you have output. Actually, I would prefer drawing it from scratch. Input and output. Okay, so when you have zero, we're dealing with a CMOS inverter. When you have zero input, you are literally here, zero input. What do you expect as an output? VDD, right? Of course. So this is my output. On the other hand, when you have VDD as an input, what do you expect as an output? Zero. Like this is where you're supposed to be. So you got 2 points. Here is one, here is the other one. But tell me something. Let's put some number here. Imagine our VDD is 0.8 volt. This VDD could be anything, 10 volt, 5 volt, 2 volt, depending on the technology, right? Okay, so if your VDD is 0.8 volt, and if I apply 0 volt, you get 0.8 volt at the output. That's easy. But if I apply 0.1 volt, what happens then? What should happen? I mean, if you were a circuit, would you treat 0.1 volt to be a high voltage or low voltage? Low, right? No, it's almost zero. I don't care. I'm going to give you what? 0.5 VDD. If I give you 0.2 volt, still low. Like, I don't care. It's low, very low. I'm just going to treat it as zero. And so on. How long, logically, would you continue treating that level to be lower? Logically. Thank you. Yes, at least, I mean, if you are fair, at least up to VDD over 2, which is 0.4, as long as you don't cross that limit, anything that's below half of VDD should be treated as low input, and you should be creating high output. Does that make sense logically? And the moment you cross, if I give you 0.7 volt, 0.6 volt, 0.75 volt, all of them should be treated as higher voltage. And you should create what? Zero at the output. So essentially, all on a sudden, I should flip from here to there. So this is what I expect from an ideal inverter. As long as you don't cross the limit, like VDD over 2, I'm going to keep doing what I was doing. Stable. And the moment you cross the limit, I'll do the exact opposite thing. So this is what an ideal inverter should look like. And that's what you see here in the red line. This is an ideal inverter. And exactly at VDD over 2, you have a switching. You can have a switching. But the world is not ideal, as you can imagine, right? So the blue one is what you get, essentially. The blue one is what you get. But it's pretty close to ideal, as you can see, right? If you design the CMOS inverter circuit really well, you can get as close to the red line as possible. So that's the dream combination. You can design really nice NMOS and PMOS transistors so that it becomes close to the red line. But practically, it's not going to be exactly identical. Now there comes the question. I asked someone, why do you think we have this tapering kind of effect? Why do you think we have this, gradual transition rather than like a abrupt switching? Yes. Right. Yeah, right. Perfect. Yes, exactly. So did anybody else? You can still try. Did you understand his answer? I told you that. I mean, this was idealistic, and I kind of pointed it out politically as well. That okay, ideally, when you apply a voltage, like high voltage or low voltage, NMOS turns on, PMOS turns off, and vice versa. But you don't just go from 0 to VDD without going through all the other levels, do you? Right? Say, for example, if I try to go from 0 to VDD, I mean, will I just hop from 0 to VDD? No, I'll gradually charge up my input from 0. So I will have all the other intermediate voltages. What happens then? What happens for VDD over 2? There will be situations where both NMOS and PMOS will be on momentarily, but obviously, hopefully not for too long, but for some time, they will be on. So it's not really perfectly identical as or perfectly ideal as we hoped initially. Okay, that's the main reason why we have this non-ideal type of transition, because the transistors have mixed mode operation. They are not just cut off to cut off, like one of them cut off and then other one cut off. No, There will be situation where both of them are on together. Okay. All right. The reason I said that is somebody answered that, oh, it takes some time to charge and discharge. Well, that's not for this diagram, is it? That's for which one? Because when I say it takes time, how do you see time when you don't plot the time in the axis, right? So there is no time here. It's not a time signature. It's literally because of the other reason. Okay. And trust me, these seemingly simple questions, like that sounds childish, are very popular for interviews. How many of you have tried any internship interviews with any tech industry or semiconductor industry? Right? How were the questions? Did they ask you something super tough, super difficult? I don't know your experience. Well, yeah, right before they want to hire you, they start all those other stuff. But yes, but initially they will always ask you simple stuff, like stuff like this, super simple. They want to, because if you get stuck there, there is no point wasting time with other complicated things, right? That's the reason. So getting your concepts clear. Oh, by the way, the answer to that question is right here in this slide, which I already discussed. In these points, you have both NMOS and PMOS transistors on. Notice only at the extreme, at this extreme and the other extreme, you have PMOS completely off, NMOS completely off. Notice that? But in all the other points, they're both active. May not be like the most powerful version of them. One of them is saturated, other one is linear, but that is okay. They're still active. So that's the reason why you have some sort of tapering effect. All right. Anyways, yes. Mhm. Mhm. Sure, it's a good question. So apparently, when you see, let me go back here. When you see this ID versus VDS characteristics, and I told you that this is linear, this is saturation. Okay, where does it saturate? My question. Do you know like who determines where it saturates? There is a VGS involved as well. So in older technologies, wherever VDS becomes equal to VGS minus V threshold, that's where you get this saturation. Okay, so there are two factors at play. First of all, VDS is a factor and VGS is a factor. So it's not easy when you put two transistors, NMOS and PMOS together, because their VGS and VDS are changing simultaneously. Here is how. Let me show you. So this is your output. When your out, like the capacitor charges up or discharges, your these node voltage changes. Would you agree? This is drain for the NMOS and source. Whenever this output changes, your drain to source voltage changes. At the same time, you're changing the input from low to high or high to low. And that input is the gate of this transistor and also the other transistor. So basically, when you change the input, your gate to source voltage changes. At the same time, your output is changing. So your drain to source voltage also changes. Sorry, I think I clicked on that for some reason. Am I making sense? So you have two inputs simultaneously changing. So therefore, this complex situation, right? It's not a standalone transistor. Make sense? Okay. All right. Before we move on, one other quick celebrity point to point out. By the way, I just, realized that I was treating 2:30 to be the, end point of the. I don't know why I thought about it. Honestly, I was like literally laughing after this. Anyways, so the point is there is a important parameter which will be useful for our SRAM design as well. It's called logic threshold voltage. Okay, and ideally, what do we mean by logic threshold voltage? We just discussed logic threshold voltage together. I told you if VDD is 0.8 volt, how long would you treat a voltage to be low? You said 0.4 VDD over 2. That's your logic threshold voltage. wherever the logic flips. But remember, that's considering that NMOS and PMOS transistors are perfectly balanced. But honestly, it's very difficult to achieve perfect balance. So there will always be some asymmetry. NMOS more powerful, PMOS more powerful. So there is a chance that your switching point could be towards lower than VDD over 2 or above VDD over 2. There is a possibility that it will not be exactly VDD over 2. Make sense? How can you calculate that? So if you get the VTC, voltage transfer characteristics, draw a 45-degree line. And wherever it intersects, the point corresponding to that would be your logic threshold voltage. So let me show you one more thing here. So imagine this is VDD. This is VDD over 2. Okay. Now, this is your VTC, voltage transfer characteristics. V in or whatever. This is V in, V out. Doesn't matter. Now, when you draw a 45-degree line, basically shows that, oh, VDD over 2 is my logic threshold voltage. But it is possible to move the VTC willingly by design, by circuit design. Move the VTC here. Let me name that. This is B. The red one was A. This is B. Now, what would be logic threshold voltage for B? Less than VDD over 2. Does that make sense? And can anybody tell me how can I manage to get B from A? What changes should I, bring to A to get B? Great. Yes. Thank you. That's definitely one. There are other ways as well, but that's probably the easiest one to do. You can always make the transistor sizes asymmetric. Maybe make the PMOS bigger, NMOS smaller, or vice versa. But can you tell me, what was done here? Whose size was changed? NMOS or PMOS? And when I say changed, what kind of change? Did I increase the size of the NMOS? Did I decrease the size of the NMOS? And what did I do? Is there any way to figure out logically without memorizing or without going through the book? Yes. Uh-huh. Yeah, perfect. Perfect. Thank you so much. Yes, exactly. So notice, who takes a node voltage down to ground? NMOS or PMOS? NMOS. So notice that this guy was so busy and so eager to get down to 0. Why is that? The NMOS must be more influential. You see, NMOS is more influential here. So you must have made the NMOS bigger. More width, more current. Remember, more current, more power. How do we know more width, more current? So a very simple way to, remind you, take a look at this current equation. Doesn't matter whether it's linear or saturation. Width, if you double the width, you get double the current. Simple, right? At the very least. Okay, so there you go. This is how you can logically understand what's going on with this. Or as a circuit designer, you can decide, oh, I need to shift slightly to the left. Sure, increase the NMOS size and vice versa. Okay, now moving to the next slide, another important concept about inverter. And by the way, I don't know if you have noticed, have anybody taken 433 with me? So, okay, so we did cover almost all of this, right, in 433. But I'm not covering everything that was covered regarding an inverter. I'm picking and choosing things that will be useful for SRAM specifically. So this VTC is definitely necessary. It's a must-have component for SRAM understanding. Number 2, regenerative property. So basically, regenerative property is the fundamental reason why SRAMs are stable memories. And I'll explain that. So just bear with me for a second. What does it mean? Imagine that you apply a voltage as an input here. Okay, so let me just pick some number. This is V0, this is V1, V2, V3, V4, blah, blah, blah. Right, there is a chain. So you have a chain of inverter. When you apply a voltage which is not perfectly VDD, notice this is 3 volt. Your VDD is 5 volt. So it's not perfect, but you can tell that it's supposed to be high because it's more than 2.5 volts. So more than VDD over 2, I mean, like 10 seconds. Okay, we'll be done, at least with this slide. Are you guys still with me? Okay. So basically your input was not perfect. It was degraded. We say that it was a degraded input, but it at least could tell us that it's supposed to be a high input. So if this is VDD, this one should be 0, the other one should be VDD, another one should be 0, and so on, right? Notice if V0 tends to be higher, V1 immediately goes to 0. This is 0, by the way. So the next inverter will have no idea that there was a degraded input, right? The next stage will behave perfectly, and the stage after that will behave perfectly. So even if you have a faulty input at any node, the inverter will recover. Sorry, it will recover and regenerate. That's called regenerative property. And I'll explain why that is in the next class, maybe in next week. This is where the explanation comes in. But at least you know that this is what regeneration means. Okay. All right. Thank you. I hope it's 2:40. Yeah.